Hello, this is What is Electricity, Part 4. I'm Aaron Jerome with Jerome Electronics. I think I'll dispense with the music at the beginning. It didn't sound that great, and I'm probably going to have to edit out of the other videos. Sorry about that. I got a lot of music I like. So anyway, this is Part 4. Let's talk about what we've been discussing. So far, we've been discussing what is a basic circuit, simplified Ohm's law math, resistance to the flow of electricity, introduction to circuits, simple circuit analysis using Ohm's law, circuit analysis using Kirchhoff's series laws, series versus parallel circuit analysis using Kirchhoff's parallel laws. We're going to talk about this time what kind of a name is Kirchhoff. We're going to practice some series circuit analysis. We're going to talk about what is power. We're going to practice, I don't know if we'll get to these this time, but we will be practicing some final exam style series circuits and also some, well, just one of each. Simple circuit analysis using Ohm's law, circuit analysis using Kirchhoff's series laws, series versus parallel. Don't think I'll get to all of these this time. Just hoping to make it's probably be brief, more brief than others. But let's carry on. And whatever we don't catch, we can catch later on in another presentation. So, who was Gustav Kirchhoff? So, I have an assertion that is probably wrong, and I have some information that is correct. First of all, he lived from 1824 to 1887. He was a German physicist, and I think he was a possible Time Lord. If you don't know, I claim to be a Time Lord. I've never met him in my time travels, but how do I know he's a Time Lord? There's two things about this man that convinces me that he might be a Time Lord. Of course, you don't have to believe that. First of all, anybody that was born between 1824 and 1887 did not have headphones to listen to their music, but you can see the wires to his headphones hanging down. So that's one evidence. Another evidence is he has helmet head. How do you get helmet head? Well, you wear a helmet. Why do we wear a helmet? So we can ride our motorcycles. But they didn't have motorcycles between 1824 and 1887. So, of course, I could be wrong about this. Pronunciation. His name is generally pronounced Kirchhoff, or Kirchhoff, probably more Kirchhoff. I usually pronounce it wrong. Sometimes Kirchhoff. I've heard lots of both ways. Not only did he develop the laws we've been using, but also he was a large contributor to quantum theory. He developed the black box theory of radiation that led us to realize that atomic radiation was not continuous, but occurred in packets, implying the existence of atoms and electrons. So, genius. He's a genius. Okay. If lamps were the resistors, they'd be represented by the squiggly lines in this circuit. And let's just say we have this. This is actually called a schematic of a circuit, which uses schematic symbols to represent a real circuit. And by the way, I have made, I don't imagine it'll be too difficult, but I've made a handout of this in the next 3 slides for students to use. Pardon me. But now that you know all of Kirchhoff's laws and also Ohm's law, the idea is to look at this circuit and be able to fill in the blanks. But there is some explanation that is needed still. First of all, this gap here currently it just represents this is where the battery or the generator goes. So just imagine that it's hooked up to a battery or generator. And the battery or the generator is also known as where the total of each of these properties is. So the electromotive total, that's volts, the resistance total, and the intensity total, that's amps. Okay, so these are where the totals are, and then each load or resistor has its own group because each one of these consumes voltage. In this case, this resistor at the top is known to consume 12 volts of voltage. It is a resistor that provides 24 ohms of resistance, and we want to know the intensity. Over on the right side is a resistor that consumes 10 volts, so we would say the voltage drop is 10 volts. It has a resistance of 20 ohms, and its intensity we don't know, but we're going to figure that out. Over here we have voltage of 2 volts. Resistance here at this location is 4 ohms, and we need to know what the intensity is. Now, I don't actually fill in all of these blanks because it is my intention that the students do it before I do, and if they do, then they own this information. You students, if you can do this, you own this information, and you can feel more confident about being able to do this before tests and so forth. Okay, so how do you figure this out? Well, first of all, we know that this is a series circuit because there's only one pathway, whichever direction the electrons are going. There's only one pathway, and every electron must go through every component. It's a series circuit. Otherwise, there would be branches or choices for the electrons to choose different paths. This is a series circuit. What that means is we're going to use Kirchhoff's series laws to figure this out. That means we'll be using KSLV for voltage, which, if you remember, is add them up. So all we have to do is add for volts 10 plus 2, that's 12, add 12 more, and our total is going to be 12 volts. We can do the same thing for resistance because KSLR is also add them up. So 20 plus 4 is 24, add another 24, that's 48, the total resistance is 48 ohms. Intensity, we're going to have to use Ohm's law. But I thought I put it here. I guess I didn't. Okay, where's the stuff? There it is. Okay, so for intensity, we're going to have to use Ohm's law. That's pretty easy because you know two pieces of information. Voltage always goes in the top. Resistance goes down in the lower right quadrant, 12 divided by 24. Be careful. A lot of students look at this and say, oh, that's half. Yeah, and that's right. But some other students, they think, oh, that's two 12s that live in a 24. No, that's not how to do division. The volts go in the top. The resistance goes down below. So you hit a 12. You hit the 1, 2 keys, then you hit the per line button for divide, and then you hit the 24, and you realize that amps are 0.5 amps. Now, the final answer probably should be converted to engineering prefix notation. We won't do that on this one. But also, if you remember KSLA, KSL amps for intensity or current, if you know one of these, then you know it's the same everywhere. So 12 divided by 24 is 0.5 amps, and 10 divided by 20 is 0.5 amps, and 2 divided by 4 is 0.5 amps, and 24 divided by 48 is 0.5 amps. So if you got that before I did, then you're probably doing pretty good, and you'll probably do well when you see questions like this on one of the assessments. Here's another one. Now notice, this is in engineering prefix notation, which is fine, and that is how you want the answers. This happens to be in base because that's the best notation. This is 2.2 k ohms, 1.6 k ohms, 1.2 k ohms. But if you ever put this information in a circle T, make sure that you do not mix prefixes with other prefixes while doing math, or you'll get the answer wrong. Be careful about that. Okay, so we could add this up. I like to think of this as money. Remember, resistance, KSLR, add them up. That's the only information we have around here. We have 12 volts over here, but we don't know what the resistance is. If we did, we could divide 12 by that resistance and find the intensity, and then the intensity, or amps, if you know one, you know them all, so that would be the same all the way around. What's the total resistance? Total resistance is add them up. So $1.20 plus $1.60, that is $2.80. $2.80 plus $2.20 is $4. So the answer here then would be 4 k ohms. But if you wanted to find the intensity, you're going to have to divide by 4,000 ohms, taking it out of prefix notation, putting it into the base notation. So 12 divided by 4,000 will give you, trying to remember, I might have to actually get a calculator and look at this. Let's take a look. Let's see. Do I have my calculator here handy? Here's one. I'm hoping you'll be able to see this. Here's my calculator, and I know that it is resistance of 4,000, so 12 divided by 4,000 equals 0.003, so that's 0.003. I hope I did that right. It's not what I remembered, but maybe I'm remembering another one. Let's do it again. Equals, that's just going wonky on me now. So, okay, so 4,000, which is the 4k ohms when you add up all these ohms, divided, no, that's wrong. That's wrong. Got to divide the 12 first. That is a common mistake. 12 divided by 4,000. See if we get the same answer. It is 0.003. If you convert that to engineering prefix notation, you would move that decimal 3 places to the right. And so it would be, and when you do that, it would make it milliamps. So 3 milliamps would be the answer here. But if you know the ohms if you know the amps in one location on a series circuit, you know the amps in every location. Then to find the remaining voltages, you would have 2 out of 3 pieces of information for each of these, and you would use Ohm's law to figure out the missing piece of information. I hope that you're understanding that okay. Now, was it 4 or 5? Now, my notes here say it might have been 5,000 ohms. Let me do the math again. 1.2 plus 1.6 is 2.8. Yeah, I messed up. Let's do it again. That's my problem. I think too fast sometimes. So we have 12 divided by 5,000, and we have 0.024. Now that is the number I remembered, and guess I messed it up. But I always tell my students, I make more mistakes than you do. You guys have to correct me sometimes. But I've made so many mistakes, and I'm so old that I don't care anymore. As long as I learn from them, that's the important thing, and students shouldn't be bothered by that either. Make a mistake, learn a thing. That's good. That just means your brain gets bigger and you evolve and you become, well, less uninvolved, more evolved. I don't know how to say that. Okay, so it's 2.4 here. And that means it's 2.4 amps all the way around. 2.4, that would be milliamps. It's 0.0024 amps, or 2.4 milliamps after you've converted into engineering prefix notation. And that's the same all the way around. And then you can put these, take them out of prefix notation, put them into base. In this case, it will work either way. So 2.2 kilo ohms times, no, it's actually 2,200 ohms times 0.0024 amps will give you this voltage. And then you do it again over here, you get this voltage. You can do it a third time to get this voltage, but you could also subtract the 2 voltages you have from the voltage that you know is the total and get the same answer. Okay, now I'm done confusing myself. Hopefully I didn't confuse you too much. I did catch my mistake. That's a good thing. Let's go to the next one. Maybe. Oh, I got to click this thing. Next one. Okay, I guess I'm showing you what I meant. It's 22, 16, 1200. If we add all of those up, we're going to get 5,000 ohms. And 5,000, we put that in the circle T, 12 volts divided by 5,000 ohms is 0.0024 amps, which is the same thing as 2.4 milliamps. Here's another one, thankfully. Okay, what are we going to do with this thing? Well, the easiest thing is to recognize that we know the amps in one place. KSLA says if we know the amps in one place, we know the amps in every place. It is 5 milliamps all the way around. But look at this. This resistor is 10 volts with 5 5 milliamps, and this resistor is also 10 volts with 5 milliamps. These two resistors are identical, so once you figure out one of them, you actually know the resistance of both of them. You can subtract that resistance from the total resistance to find this resistance here. If you do, you'll have all three resistances, and, well, you'll have all the information. I guess the last thing you need to do is add, well, because KSLV, add them up. 10 volts plus 10 volts, that's 20 volts. 5 more is 25. You got 25 volts here. So now I'm doing this fast. I'm kind of hoping you have stopped the video here if I go too fast. Try to figure it out yourself. There is one more here. You could stop the video and try to figure this one out as well, but I'm not stopping. I'm going to keep talking. So we have the easy one. We know that the amps is 9 milliamps, and KSL is another series circuit. So KSLA says if you know any one of these amps, you know every amp. So we would just put 9 milliamps here, 9 milliamps here, 9 milliamps here, and not go to power, but 9 milliamps here. Once we've done that, we have 2 pieces of information out of 3 for every location. And to get the total resistance, we can add up these amps. 40 cents plus 120 cents is 160 cents. And 160 cents plus $2 more is 360 cents. And 60 plus 44. This is 4K amps. No, not quite ready yet. 4,000 ohms or 4K ohms would go here. We know all the ohms. We know all the amps. Ohms are add them up. Amps, if you know one, you know them all. And volts, they're usually add them up, but we don't have any of them to add up. So we can calculate each one of those using Ohm's law, putting in the 2 pieces of information that we have for each one of these, and finding the amps at each location. Add that up or use Ohm's law again here, and that will give you the total amps. All right. I guess I'm jumping at the gun to talk about what is power. Now, that is a play on words, so pun is intended. This is James Watt. James Watt lived in the late 1800s. He was an engineer and innovator from Scotland. And he's trying to make steam engines better or more efficient. So he came up with a steam engine design. This is a steam engine design, and I think it's fascinating to see it rolling along. And just think we got a sealed pot of boiling water somewhere off to the side, and it's emitting steam, and steam's going down this pipe, and we can increase or decrease the flow of steam with this valve. But there's another valve below that one that is actually controlled by this whirligig right here. And just like when you hold your arms out when you're spinning on a chair or spinning on the ice, you slow down, but when you pull your arms in, you go faster. Same thing. These are heavy metal spheres here. And what they do is govern the speed automatically of this steam engine by putting their arms out to slow down. When the speed gets too high, they put their arms out to slow down. When the speed gets too low, they'll let their arms in. And so that regulates the speed. The steam comes in, and as this slider slides back and forth, the steam will go down this pipe and push this piston to the side, to the right. And then this slider goes the other way, and steam comes down on the other side and pushes this piston to the left. And that causes this piston to go back and forth. And of course, the used steam comes out the top here. And that piston pushes this rod here, and it turns the wheel. And that's the simple method for making a steam engine. But James Watt, he wanted to apply a number to a steam engine to talk about how efficient it was. And so once he had a number that indicated the efficiency, an efficiency index, then he was going to work with steam engines and see if he could make one more and more and more efficient. So to get that number, he thought about it for a long time. He wanted a number to compare the efficiency of steam engines. Better number can lead to better steam engine. So his solution, which I'm not having my students write down because well, we don't use this equation, but his solution was force times distance equals time, and that turned out to be what he called the power equation. It was later named watts in his honor. Force of what? Well, you can actually, if you have this piston push against a bathroom scale, you could actually measure the force of the push of the piston. That's what we mean by force. You could measure it in several different places along this rod, and he probably devised a very ingenious way to measure the force as this thing is running, the force of the steam, for example. Okay. He then multiplied that by the distance of travel of the piston, and then he used a stopwatch and he timed how long it took for the piston to go one direction. Force times distance times time is the equation for power. In electronics, we have an equivalent equation for power, and that's what I want you to write down. The solution for electricity happens to be volts times amps, and it is equivalent. Its result is equivalent to the other equation, which means we could set these two equations equal to each other. And if we had four pieces of information, any four pieces of information, we could combine them to find the missing fifth piece of information. So if we had force, distance, time, and amps, for example, we could calculate the volts of electricity required to power this engine. We could talk about it in terms of volts instead of force, I guess. That's what we're talking about. In electricity, it's volts times amps. Now, that is important, and you do need to write that down because we're going to use that equation here real soon. And I believe, let me check here. Yeah, I believe that's all I wanted to say. I'll give you a quick preview of where we're going next. It's a final exam prep question. Has to do with circuit analysis. So if you want to stare at this for a long time and figure out, because you have enough information to figure out the total watts at the first resistor. In fact, you have enough information to fill in all of these blank boxes. But for this particular test question, I just want to ask how many watts are being consumed. And again, you have all of the equations. Let's call this presentation good for now, and we'll come back with a fifth part where we talk about all of this. Talk to you later.